stargazers and astronomers are shocked by the impending disappearance of the North Star, Polaris. This event is anticipated to be the next big thing in the world of astrophysics. Yes, you heard that right. Polaris is about to be rubbed off our starscape for good, and this impending celestial cataclysm carries profound implications for our ground-based telescopes, which use it as a reference point for their calibration and accuracy. Brian Cox warns that the Polaris explosion is imminent and will change the night sky forever. Let's delve deeper into the story of the North Star and why its end matters so much. For millennia, Polaris has been a celestial guide for both astronomers and navigators, but all of this may change in a matter of decades, if not years. A recent research work presented to the esteemed Royal Astronomical Society in September 2023 has all but sealed the fate of this guiding light. Polaris is on the brink of a cataclysmic event, an explosion that could result in its disappearance from the night sky forever, altering our cosmic compass. But before we delve into the potential consequences of this revelation, let's explore the star in question. Also known as the North Star or Pole Star, Polaris holds a special position in our night sky due to its proximity to the celestial North Pole. It sits almost directly above the Earth's North Pole, giving the illusion of being almost stationary in the northern sky. Positioned in the Ursa Minor constellation, which is also known as the Little Dipper or the Small Bear, Polaris shines as a moderately bright yellow-white supergiant star. It outshines the Sun in luminosity, radiating considerably brighter across the cosmic canvas. Moreover, in terms of sheer size, it dwarfs our Sun, boasting a radius estimated to be about 40 times larger. Despite its apparent singularity, Polaris is part of a complex triple-star system. Two of these, Polaris AA and Polaris AB, appear as a single star to the naked eye. A third companion, called Polaris B, orbits this binary pair. The intricate gravitational interactions among these stars influence their orbits and luminosity. These intricate dynamics can cause irregular variations in the star's brightness and pulsation patterns. Yet the exact mechanisms behind these interactions remain a cosmic enigma. On top of all of this, the awe-inspiring distance of Polaris from our planet adds a fascinating temporal twist to our understanding. Since it is 323 light-years away from us, the light we perceive from Polaris today embarked on its interstellar journey over 3 centuries ago. If we were to see Polaris explode at this very moment, it would have actually done so all those years ago. The Earth 323 years ago was quite different. In the early 18th century, humanity was navigating through a period marked by significant historical events and cultural shifts. It was an era marked by the end of the Renaissance period, the beginning of the Enlightenment, and the dawn of the Industrial Revolution. In some parts of the world, scientific advancements were gaining momentum, with figures like Isaac Newton forever changing the scientific landscape. In terms of daily life, society was still largely agrarian, with farming being the primary occupation for most people. Urbanization was gradually picking up, leading to the growth of cities and the expansion of trade and commerce. Culturally, Baroque music and art were finding prominence. So if Polaris explodes tomorrow, it would have actually done that at a time when Earth was amidst a period of transition, exploration, and change, setting the stage for the development that would shape the centuries to come, not unlike how this event would change things for our future. Throughout the centuries, the North Star has weaved its significance through the tapestry of civilizations across the ages. This stellar beacon served as a guiding light for ancient seafarers and travelers, illuminating their paths across vast oceans and unknown terrains. Polaris is a dependable reference point, guiding explorers in the Northern Hemisphere, enabling them to chart courses with confidence. Polaris has embodied a cultural and navigational cornerstone for ages and shaped the narrative of ancient explorers, storytellers, and scientists alike. So how do we know that the star is nearing its end? Classified as a Cepheid variable star, Polaris has very specific stellar properties and cosmic measurements. Its predictable brightness fluctuations have been instrumental in unraveling mysteries about variable stars and calibrating astronomical instruments. These rhythmic pulsations have traditionally followed a reliable pattern, aiding astronomers in predicting its behavior with ease. However, in the aforementioned research paper, scientists uncovered a deviation from this expected pulsation cycle that has startled the astronomical community. Polaris has taken on an erratic and unpredictable rhythm of dimming and brightening. This irregularity has prompted intense scrutiny, with astronomers grappling to understand this celestial anomaly. This departure from its norm has sparked concerns among scientists, hinting that Polaris might indeed be approaching the twilight of its existence. Polaris's pulsation period has recently begun stretching. The star was previously stable in its cyclic brightness shifts, but now astronomers have noted a progressive lengthening of the pulsation duration, with an annual increment of 4.5 seconds. While seemingly minute, this alteration holds substantial cosmic significance, signifying a substantial departure from its established behavior. There have been several speculations on the matter. Some attribute this shift to gravitational interactions within the Polaris star system. These interactions could be altering the star's atmospheric conditions, directly influencing its pulsation patterns, or more specifically, how we perceive them. However, dissenting voices in the scientific community propose a much more alarming possibility: the star is dying. Whether it's a consequence of gravitational interplay or a harbinger of an impending stellar explosion, the irregularities in Polaris's behavior have ushered in a new era of cosmology. Either way, the truth is set to change everything we thought we knew about triplet star systems like Polaris. Speaking of how revelations change our worldview, it was in 2006 that we got a close-up look at Polaris, courtesy of the Hubble Space Telescope. Astronomers also unveiled the elusive companion star nestled so intimately close to Polaris that it had been impossible to observe it beforehand. This was the first ever photograph of our celestial neighbor, capturing its ultraviolet light. Today, we know that the companion, Polaris b, orbits the core duo at a distance of approximately 2 billion miles. Although astronomers had inferred its existence from light analyses of the triple star system nearly 50 years ago, its faintness compared to Polaris obstructed direct observation until the Hubble Space Telescope made it possible. This all began with the launch of the Hubble Space Telescope, HST, in 1990. Its deployment opened a window to the universe, providing unparalleled clarity and redefining our comprehension of astrophysics. The HST captured celestial marvels that reshaped our fundamental understanding of space. Among its iconic achievements stands the awe-inspiring image known as the Pillars of Creation in the Eagle Nebula, which houses colossal columns of gas and dust where stars are born. Another landmark moment came with the revelation of the Hubble Deep Field, a seemingly empty patch of space that, upon closer scrutiny, was teeming with thousands of galaxies. This one image expanded our perception of the universe's sheer vastness and complexity forever. The HST also studied exoplanet atmospheres and unveiled tantalizing clues about their composition. The presence of elements like water and organic molecules in these far-flung realms hinted at the tantalizing potential for habitability beyond our solar system. Building upon the legacy of Hubble, its successor, the James Webb Space Telescope, JWST, was launched to push the boundaries of technological innovation further. With lessons learned from Hubble's endeavors, the JWST stands poised to propel us deeper into the mysteries of the universe, continuing the legacy of exploration and discovery initiated by its esteemed predecessor. One of the JWST's standout features is its unparalleled ability to capture celestial vistas with striking clarity, banishing the obscure shadows that once clouded our cosmic observations. The telescope operates primarily within the infrared spectrum, piercing through cosmic dust veils and unveiling celestial treasures previously concealed from human sight. At its core lies a colossal 6.5-meter primary mirror composed of 18 hexagonal segments, dwarfing the Hubble's mirror in sheer size and sophistication. Positioned approximately 1.5 million kilometers away from Earth at the second Lagrange point or L2, the JWST gracefully trails Earth's orbit around the Sun. From there, it gives us an unimpeded and steady gaze into the cosmic web. Yet, the voyage into the cosmos isn't merely a journey across light years, it's a journey through time itself. The JWST employs state-of-the-art infrared instruments capable of peering back billions of years into the past, capturing the ancient light emitted by celestial entities as the universe expands. This light undergoes a transformation known as redshift, shifting from its original visible spectrum to the infrared wavelength, or longer. The JWST is perfectly suited for detecting and deciphering these infrared signals from distant celestial bodies. And now it is all set to revolutionize our understanding of Polaris as well, as soon as it reveals clearer than ever images of the triplet star. This innovative telescope has heralded a new era of astronomical exploration, poised not just to unveil the distant reaches of the cosmos but also to unravel the mysteries of our cosmic past. With its extraordinary capabilities and unique vantage point in space, the James Webb Space Telescope stands as a beacon of human ingenuity, unlocking the secrets hidden within the celestial expanse. So far, we know for a fact that there are intriguing parallels between Polaris and Betelgeuse in that both of these giants are said to be nearing their ends. Betelgeuse is a prominent star in the Orion constellation, and it has showcased perplexing irregularities in its luminosity, much like what we observed in Polaris. This resemblance has prompted experts to contemplate the possibility of an imminent explosion, echoing concerns raised about Betelgeuse's inevitable fate. The uncanny similarities between the fluctuations in brightness and patterns exhibited by both stars have drawn attention from experts worldwide. By the end of their lives, stars often display such erratic behavior. Despite their historical regularity in pulsations, these celestial entities undergo peculiar changes in luminosity as they approach the conclusion of their cosmic odyssey. NASA has heavily scrutinized Betelgeuse's anomalies and sounded the alarm. However, the agency's heightened concern regarding the potential explosion of Betelgeuse stands in stark contrast to their lack of interest, apparently, in Polaris. While NASA has devoted considerable attention and vigilance to Betelgeuse's unusual behavior, a similar level of scrutiny and official concern has yet to be declared regarding Polaris. In any case, the intriguing parallels between these two celestial phenomena offer a captivating glimpse into the mysteries of stellar evolution. As astronomers navigate through these cosmic anomalies, the striking resemblances between the behavioral changes of Polaris and Betelgeuse raise serious questions about the nature of these stars and the inevitability of their celestial fates. Stars undergo distinct phases in their evolutionary journey, beginning as newborn stars with subdued temperatures and brightness. They progress into the main sequence phase, where they burn through their hydrogen fuel via nuclear fusion for billions of years. However, as their hydrogen reserves dwindle, they transition into the red giant phase, characterized by a luminous surge in temperature and brightness. This red giant phase is the prelude to a spectacular cosmic finale. This is usually a catastrophic explosion known as a supernova. However, some stars shed their outer layers in a dazzling display minus the massive explosion, leaving behind a dense core called a white dwarf. Concerning Polaris, scientists have proposed that the star has started on the stages of helium depletion, as seen in most Cepheid stars nearing the end of their lives. As a Cepheid star runs out of its stable helium supply, it experiences erratic pulsations, manifesting as fluctuations in its luminosity. This depletion triggers a sequence of events resulting in irregular light emissions, as seen in Polaris. However, while these irregularities do align with behaviors typical of Cepheid stars approaching their twilight phases, concrete evidence of Polaris entering the ultimate stage of its life cycle is yet to be unveiled. Astronomers are scrutinizing and deciphering these irregularities to unravel the impending fate of Polaris and gain deeper insights into the enigmatic behaviors of such stars. But if Polaris were to undergo a supernova event, it would be a breathtaking spectacle for all to watch. Abruptly blazing with intensity, it could even surpass the Moon's luminance, emerging as one of the most radiant objects in the night sky for days, weeks, or even months. The transformation of Polaris during this cosmic upheaval would also be very dramatic. It would display vibrant hues before gradually dimming away. This celestial spectacle might temporarily disrupt the familiar arrangement of the Big Dipper or Ursa Minor, given Polaris's current role as the North Star and its integration into these iconic constellations. As for our safety here on Earth, there's no need for concern. Considering Polaris's distance and mass, Earth would likely remain unharmed even in the event of an explosion. While a Polaris supernova might not dazzle as prominently as one involving Betelgeuse, it might still persist as a spectacle to the naked eye for quite some time. The scientific community, astronomers, and observatories worldwide would undoubtedly be captivated by this phenomenon. And while there won't be any direct impact on Earth's atmosphere or immediate surroundings, the death of Polaris would surely leave an indelible mark on the night sky. So what will happen to Polaris itself? Contrary to the conventional supernova closing chapter for massive stars, Polaris is unlikely to meet this explosive fate. Ordinarily, when massive stars undergo supernova, it results in a colossal explosion. This cataclysm disperses heavy elements, resulting in the birth of neutron stars or black holes. This is after the core collapses in high-mass stars, around 8 times the mass of our Sun. When such stars run out of their nuclear fuel, they collapse under their own gravitational force, triggering an intense and violent explosion. Supernovas are broadly categorized into Type 1 and Type 2. The latter occurs in massive stars with complex layers, where the core collapse causes the explosive expulsion of outer layers, emitting a burst of energy and light visible across vast distances. However, a Type 1 supernova happens in binary star systems and a white dwarf, leading to a sudden fusion reaction when the white dwarf accumulates enough mass to undergo the supernova explosion. Supernovas serve as standard candles for measuring cosmic distances, helping us estimate the universe's age and expansion rate. Post-supernova, a star's core collapse can give birth to either a neutron star or a black hole. A neutron star is the dense, compact remnant left behind when a massive star exhausts its nuclear fuel and undergoes a supernova explosion. Neutron stars are incredibly small in size compared to their original stars, packing a mass several times that of our Sun into a sphere with a diameter of about 12 miles or 20 kilometers. The intense gravitational force on a neutron star is so powerful that it squeezes protons and electrons together, forming neutrons. This leads to extraordinary density, so much so that a teaspoon of neutron star material on Earth would weigh billions of tons. A black hole, in contrast, is a region in space where gravity is so intense that nothing, not even light, can escape its gravitational pull. The core of the dead star collapses to a point of infinite density known as a singularity, surrounded by an invisible boundary called the event horizon. The event horizon is the point of no return. Once something crosses it, it cannot escape the black hole's gravitational grasp. Despite their mysterious nature, black holes can indirectly reveal their presence by influencing nearby matter. For instance, when a black hole is part of a binary system, it can pull matter from its companion star, creating an accretion disk composed of gas, dust, and other debris that emits X-rays before disappearing beyond the event horizon of the black hole. But here's the deal: Polaris has a mass approximately 5 times greater than our Sun, and thus falls short of the magnitude necessary for a supernova. Instead, when it finally exhausts its nuclear fuel, it will shed its outer layers and evolve into a white dwarf. This will be a serene transition, minus a supernova's explosive display. A white dwarf is the remnant of a low or medium-mass star that has ceased nuclear fusion, compressing a mass equivalent to the Sun into the size of our Earth. Upon this transformation, Polaris will forever vanish from the night sky. Drawing parallels between the anticipated effects of Polaris's end and documented supernova occurrences in the past can help us map our expectations. Well-documented supernovas like SN 1054, Crab Nebula, or SN 1987A can help us dissect resulting phenomena such as nebula formation and the release of cosmic rays following such events. We can also evaluate potential similarities in luminosity fluctuations, elemental ejections, and their impact on surrounding cosmic environments. This way, we can lay the groundwork for understanding Polaris's potential aftermath. There is no lack of data for comparison. Analyzing light curves, spectra, and remnants from these events can help us project potential characteristics for Polaris's end, helping us predict the subsequent evolutionary stages of its celestial remnants. To make a solid comparison, scientists carefully examine the differences in the mass composition and speed of materials ejected during a star's burst and contrast it with other well-documented events. When the time comes, we'll be able to do the same for Polaris too. By investigating whether Polaris's eruption might give rise to nebulae or distinct elemental patterns, we will surely enhance our understanding of its individual characteristics. Digging deeper into the life cycles of stars leading up to their demise also involves studying the mass, metal content, and evolutionary paths of stars in the pre-supernova phases. By comparing these aspects of known supernova cases with Polaris, we can gain insights into potential differences or similarities in how they explode. Another crucial aspect involves assessing the pulsation patterns exhibited by stars nearing the end of their lives. In this area, we have made considerable progress in deciphering the fate of Polaris. This analysis helps us gauge similarities or deviations in irregular pulsations, deepening our understanding of the potential mechanisms behind the burst. Though a familiar territory, this examination reaffirms the likeness or deviation of Polaris' behavior in its explosive climax. This thorough comparative analysis will shed light on, contrast, and explore potential outcomes. In doing so, it holds the promise of providing valuable insights into the distinctive or shared aspects of this celestial event within the broader cosmic context. Embarking on the intricate journey through Polaris' cosmic is a formidable challenge for astronomers. Despite meticulous observations and exhaustive analysis, the irregularities displayed by this iconic star persist as an unsolved riddle, defying conventional explanations and casting an enigmatic aura in the celestial tapestry. Predicting the precise finale of a star's life is a daunting task. The perplexing nature of Polaris prompts a call for deeper investigation. Astronomers keenly recognize the imperative need to untangle the underlying mechanisms governing this unprecedented behavior. Unraveling the unique conditions steering Polaris' irregularities is the key to advancing our understanding of stellar evolution and behavior. Today, Polaris serves as a crucial cornerstone for telescopic calibration and celestial navigation. Naturally, it holds an irreplaceable role. The looming uncertainty surrounding Polaris' future and the potential for a catastrophic burst raise substantial concerns within the astronomical community. Revelations from the Royal Astronomical Society spotlight a new frontier demanding rigorous scrutiny and intensive research. The perplexing behavior displayed by Polaris underscores the urgency for deeper investigations and focused research endeavors. Astronomers grapple with the intricacies of irregular pulsations, recognizing the imperative to decipher the unique conditions triggering this anomalous behavior and provide a definitive answer. Yet, the ultimate answer remains shrouded for now. But it is only a matter of time. The goal of our quest is to deepen our comprehension of the mechanism sculpting Polaris' irregularities. If Polaris were to undergo a cataclysmic event, the loss of this celestial reference point could significantly impact the precision of ground-based telescopes and celestial measurements. Recalibration of instruments and potential alterations in astronomical assessments would be an inevitable consequence. The anomalous behavior exhibited by Polaris has unveiled a realm of uncertainties in the astronomical sphere. The looming possibility of its impending burst calls for heightened vigilance, concerted research endeavors, and an unwavering commitment to unraveling the unique celestial intricacies that shape its erratic behavior.